Dolphins are among the most communicatively sophisticated animals on the planet. Their acoustic repertoire goes far beyond simple navigation. Researchers have identified complex, structured vocalizations that appear to encode individual identity, emotional state, and social context. Current research, including large-scale efforts to decode dolphin communication using machine learning, suggests that dolphins may have a compositional language, not just fixed signals, but combinations of elements that carry distinct meaning. One particularly striking finding is that dolphins appear to be able to transmit their echolocation images to one another through sound. When a dolphin echolocates an object, it builds up an internal acoustic picture of that object. There is evidence that dolphins can then vocalize in a way that reproduces that acoustic picture for other dolphins nearby, essentially sharing what they see through echolocation, without the other dolphin needing to echolocate the object itself. This is a remarkable capability, and it raises an obvious question. What does that picture actually look like? That is the question this project tries to answer. If dolphins can share three-dimensional acoustic images with each other, can we make those images visible to humans? We set out to build a machine learning system that reconstructs 3D objects from dolphin echolocation clicks. Before we go any further, this project did not succeed in the way we hoped. The neural network did not learn meaningful representations of 3D structure. The classifier test we ran as a sanity check came back at essentially random chance accuracy, and the final reconstructions are largely empty or unstructured. By the standards of the goals we set, this is a failure, and we want to be transparent about that. But we still want to show what came out of it. The pipeline works end-to-end, the domain adaptation phase shows promising learning behavior, and even failed experiments produce results worth looking at. So we will walk through the approach, explain what went wrong, and then show the output. We are going to play two versions of a visualization video. The first is a direct view. Each frame shows the spectrogram of a dolphin click alongside three 2D cross-sections through the reconstructed 3D voxel grid and four three-dimensional views of the reconstruction. The second version shows the same content in a multi-panel layout, which makes the 3D structure somewhat easier to read spatially. One thing to note, there is very little visible change between frames. The reconstructions are mostly static, which is itself a symptom of the underlying problem. The network is not responding meaningfully to differences between individual clicks. Now, the approach itself. Dolphins use echolocation by emitting focused clicks and analyzing the returning echoes to build a picture of their surroundings. The challenge for machine learning is that there are no ground truth 3D labels for what a dolphin perceived at any given moment. We do not have 3D scans of the environments where the clicks were recorded. So the question becomes, how do you supervise a network when you don't have the targets? We split the problem into three phases. In phase 1, we generated synthetic training data. We created random 3D objects, spheres, cubes, cylinders, cones, toruses, capsules, and simulated the acoustic signals a dolphin would receive from each one using bellhop, a physics simulator for underwater sound propagation. These synthetic pairs, spectrogram input to 3D voxel grid target, were used to train an encoder-decoder network. The encoder processes the acoustic signal, and the decoder reconstructs a 32-cubed voxel grid from a 512-dimensional latent vector. In phase 2, we ran a classifier on top of the encoder's output features to check whether the encoder had learned anything useful. If it had, it should be able to distinguish between different object shapes. It could not. Accuracy stayed at around 10% chance level for 10 classes. That is the clearest sign that the encoder-decoder did not learn meaningful structure. In phase 3, we moved to real data. We took 392 dolphin click recordings from the ESSD dataset and applied contrastive learning. Clicks from the same recording session were pushed towards similar representations in latent space. The contrastive loss dropped from 2.35 to 0.12, which means the encoder did learn something consistent about real dolphin clicks, just not necessarily about the 3D geometry of what was being echolocated. On the technical side, the encoder is an efficient net B0 modified for 4-channel spectrograms. The decoder is an occupancy network. Phase 1 uses binary cross-entropy loss. Phase 3 uses contrastive loss. We trained on 10,000 synthetic samples. The decoder was only trained for 10 epochs due to compute constraints. That is almost certainly not enough. The acoustic simulation in Phase 1 is also likely too far from the acoustic properties of real dolphin clicks to transfer well. And without ground truth 3D data, there is no strong supervision signal at any stage. What would actually be needed for this to work? Ground truth 3D scans of environments where real dolphin echolocation was recorded, substantially more training in Phase 1, a more physically realistic acoustic simulation, and a decoder fine-tuned on real data rather than purely synthetic inputs. For now, here is what the system produces.